Yeah, I could be like explaining it here for hours and hours, but you will only remember it once you try to do it, and it's not immediately working. It never is that simple. Okay. Yeah, so once you are done with project number 1, which I hope most of you are, maybe modulo some last weeks. Generally, of course, it's a good idea to not to leave it at the last moment, because then you can still take advantage of the recitations and so on. If it's not working the last day, then it's not good, right? And there's very little time to fix that. So the next project you guys are gonna do is implementing what we talked about last time, the Gaussian elimination, and then Gaussian elimination with partial pivoting and row scaling. So you get some more MATLAB programming experience, but most importantly, solving linear systems experience. So you get to experience what sort of the solvers have to deal with, both in terms of the numerics as well as the actual implementation. And yeah, you know the drill. It's gonna be again due in 1 week. Is that cool? Okay, so what we will go through today is just some examples of linear systems, just to give you some concrete problems where solving linear systems is useful. I was saying that it's useful in many cases, but let's just look at some of those cases. And each of them has certain special properties. So what I already talked about last time is 1D interpolation. So let's recall that real quickly before I go to 2D interpolation. So the problem was given as follows. I have some four measurements, and the measurements consist of x and y axis coordinates. So I have some 4 points. The x coordinates are all different, so it's something like that. And I have just these 4 points, and I want to interpolate them. I want to figure out like what would be the value, for example, like here, or anywhere really on the real line, right? So what I can do, I can find a cubic polynomial, that's this, ax cubed plus bx squared plus cx plus d, which interpolates these x1, y1, x2, y2, and so on. So interpolating means that if I plug here the xi, x1, x2, and so on, I get back the yi, right? And even though it doesn't look like a linear problem to begin with, because you have this x to the power of 3, x to the power of 2, it actually is a linear problem. It's because the x's and the y's are known. I tell them to you, or you measure them somewhere. So then just computing the third power, well, you just compute it, right? It's just a different number. Doesn't matter, because what matters is we are solving for the a, b, c, and d, the coefficients of the cubic polynomial. And how do we solve for them? Well, we set up the system of linear equations and then solve them using Gaussian elimination, for example. And what we get is the a, b, c, d coefficients, and if we plug them here, we have this cubic polynomial that interpolates these points. So that's sort of neat, right? That's already like a useful application. Make sense? So we can also do interpolation in 2D, and actually in any dimension. In 2D it gets even more interesting. So like the setup would be that I have some points in plane. So I have a plane as usual, and somebody tells me points x1, y1, can be anywhere, x2, y2, x3, y3, and 3 more, up to x6, y6, and tells me what will be the values on these points. So for example, here could be like, I don't know, -5, or it could be like 3, whatever values. Those are the z's. And I would like to interpolate, but I would like to interpolate on the entire plane. So I would like to get a function z, which for every x and y returns me a number. So the signature of the function would be from R2 to R. So that's a 2D interpolation. Previously, I was interpolating, I had just on the x, I was just looking for a function from R to R. So that's previous slide. Just looking for a function from R to R. and here I'm looking for a function from R2 to R. So graphic, or like you could imagine, you could visualize it or interpret it as assigning colors, for example, to the plane. Like imagine I wanted to color like a piece of paper, and I had a samples of colors in some number of points. In this case, I want 6 points, because what I will want to interpolate with will be a second order bivariate polynomial. So it's a polynomial which has as variables x and y, and they are multiplied up to second order terms. So that means I have their x squared, xy, y squared, and of course the linear terms xy. Why I picked 6 points is because this polynomial has exactly 6 degrees of freedom, right? It's the a, b, c, d, e, f. So that's 6 degrees of freedom. So if I give it 6 constraints, I, in general, will be able to find a unique solution. Because we haven't talked yet about all these like corner cases, if the system like overdetermined or underdetermined. We will get there, but we are just talking about the simpler cases now. So again, I can do the same thing, right? Now you know that you should not be shying away if there are square things, because it doesn't matter, because I know the positions of these points, so I know how to compute their square, right? So I compute these coefficients. These will form for every I, for I going from 1 to 6, they will translate to a system matrix. I will not write a system matrix here because it would be a little more complicated, but you can do it for an exercise if you are curious. It'll be very similar to the previous case. But the point is that the system matrix is something I can directly compute. I can just compute the numbers. And once I have the numbers, I solve the linear system for the A, B, C, D, E, and F, where the values of Z would be what? Where do they appear in the system? The values in my samples? They don't appear in the system matrix, right? These xi squares, these guys go into the system matrix. The z's, they go on the right hand side, right? So you also can now like immediately apply all what we learned previously about LU decomposition. So if I have pre-computed LU decomposition, pre-computed the factorization, then you know we can quickly resolve for different right hand sides, right? So if someone tells me the same vertex positions but different values there, then I can resolve for the interpolating z function, the two-dimensional interpolant, very quickly. Yep. One more example is even more interesting. Like the following example. I will first explain it on the paper, and then we will summarize that. It's a stretchy rope example. It's pretty cool. It's sort of like very simple physical system. It's like a precursor to physics-based animation, I guess. In this case, everything will be completely linear. So let's assume I have like a stretchy rope thing. So I want to model like a physical object, like a rope, that's attached on some endpoints. And I model the rope as essentially as a mass spring system. So here I have some mass points which are attached with springs. And they will only be allowed to move in the y-axis, my mass points. So that's like, I'm like setting up a model now for deformable rope. Say I'm like constructing a bridge or something. Like this is like a toy example, but there is like a rope, and I want to compute the deformation of the rope under gravity and some external load. So here is how I'm setting up the problem. Actually, setting up the mathematical formulation of the problem. So my model is that each point can only move in the y-axis. It cannot move in the x-axis, just to simplify things. Here it's like a super simple model, but it's already interesting. So the coordinate of this first guy will be y1. The second one will be y2, y3, y4, and so on. And the last one will be some yn. Now I can say that this is like building, I don't know, a bridge or something. So the first two, y1 and yn, are fixed to 0. I want the end points of the rope to be fixed. Now the interesting thing is what is happening in the rope on the internal mass points. So there are going to be, so when the rope is going to like fall under gravity, something like this will happen intuitively, right? So there will be some forces acting on each of the mass points, right? So what is the simplest model for forces that makes sense? So let's look, for example, on the y2 here. So let's assume it looks something like this. So here is my y2, here is my y1. So if the first spring, the first link, the first segment is stretched like this, then there should be some force that will be acting up on it. We'll try to restore it back, right? That's my like elastic model of this link, and then this force will be what? It will be y1 minus y2 times some spring constant k. The k is telling me essentially how strong this spring is, how stiff the rope is. I can have like really mushy rope or something that's like all steel that will like really resist deformations quite a lot. So that's the point of the k. So what is important here? If y1 is above y2, then this is a positive number, so the force points up. It wants to restore. It wants to go back. It doesn't like to be stretched too much, so it wants to go back to its rest state. Now the next spring is like this. So let's assume it's like stretched like this for illustration purposes. And here is my coordinate y3. So this node here, the node corresponding, the second node, will also feel some force. So this is the force due to the first spring, and the force due to the, so maybe I'll write it here, force due to first link or spring. And the force due to the second one, what do you think will be the force due to the second spring? It's the same idea, except that now there is a mass point, right, which is connected to two springs. Each of them contribute by some force, because the springs don't like to be stretched. So if they don't like it, they tell it to the node by pushing on it by a force. You can think about it this way. So what do you think will be the force due to the second link on this node? It'll be something with I3 and I2, right? And if the I3 is above, then I will want I3 minus I2, right? Because if it's stretched like this, then the force, this is the force from the second one, will be also pointing up. In this case, will be stronger because Y3 is higher. So the more stretched the spring is, the bigger the force, right? This is sometimes called Hooke's law, a linear relationship between displacements and forces. And the K is the coefficient of that spring stiffness. So this is the force due to the second link. So we are almost done. So we'll be also assuming that this is in a gravitational field. So on every node there will be also a force pointing down, which will be the gravity force. That means minus mg, right? So m is the mass of this node, and g is the gravity constant. And it's minus because it goes down, right? My y-axis points up. I have this coordinate system. The x doesn't matter because the x's are fixed, but my y-axis points up. So if the force due to gravity pushes down, so it's minus mg, right? And to make things more interesting, on one of the nodes called IY, I will put an additional load. I will put there like some extra weight, like this, with the mass capital M. So there will be like something hanging on this rope to make it a little bit more interesting. Now this is already a relatively sophisticated, I mean, it's a brutal simplification of real physics. Real physics is way more complicated. It becomes non-linear and so on. But it already gives us some very useful insights about a system like this, about a stretchy spring. And the cool thing is that this can be totally, completely described in terms of linear equations, a problem like this. So maybe now I can switch to the slide. Now it should make more sense. So this is just describing the situation in words. So we have this stretchy rope with a number of sections. So those are like our springs. And, well, maybe not section, but we will say each node. We can assume that all the mass is concentrated at the nodes, that the links don't weigh anything. We are really making an abstraction, mathematical or physical abstraction. And the force is k times I minus 1 minus yi. That's what I was showing on that example. That's the force due to the first spring, and the force due to the second spring is k times y subscript y plus 1 minus y sub I. So the two nodes on the endpoints, the y1 and yn, are fixed. That means I am holding them at 0. So like in this, also like draw it that this is like attached to something, right? This is attached to something, there will be gravity acting on it. And these things are stretchable, so they will stretch, but not too much. They will only stretch enough to counteract the gravity. Makes sense, right? I guess intuitively. So I guess these external links, they provide just enough external force so that the y1 and yn, they stay exactly at 0. When I have something is attached, like to a wall or something fixed, and I push on it, then by the law of action and reaction, the thing pushes back by an equal and opposite force, so the force is 0 and the thing stays there. You don't have to worry so much about this physical model. This is just like setting up a non-trivial example which leads to a linear system of equations, a very important system of linear equations. So how do these linear equations look like? So for every node which is not one of the end nodes, so I mean regular node, one of them that's inside, I sum the two forces, the one from the left link and the one from the right link, and minus mg, so remember, minus mg is the force due to gravity. So if I'll do it for the first link here. So if I have a static equilibrium, it means there are no forces acting on the system, because if there were forces, it would be moving. So the total force, so this is force due to the first link, this is force due to the second link, and this is force due to gravity. They all have to sum to 0 once the system has settled, right? If you poke it with a stick, it's gonna like vibrate, but eventually the vibrations will die out and the system will be settled. That means all the forces will be in balance. The forces will be 0, it will be static equilibrium. And that's what we are looking for. That's the problem. We have this bridge model. We have some external load on one of these nodes to make it more interesting. And we are looking for what the static equilibrium of our rope or bridge or whatever it is. So the equations for the internal nodes are like this. Here I just flipped the mg, so I took the minus mg and put it on the right hand side. The node which has the extra weight, the equation is exactly the same except for that I increase the mass, right? I do lowercase m plus uppercase m. The m is the mass of the extra weight attached to that node. And obviously the y1 and yn, they are 0. They are fixed there. And this is a system of linear equations, which we can solve using the techniques we have discussed. So that's actually sort of cool, because now you can compute something interesting, right? Something that would be relatively hard to compute in different ways. You can compute some interesting shapes of the stretchy rope. You guys copy? So this equation, actually this equation can be rewritten. So I can divide by k, right? And if I divide by k, I get this mg divided by k. So this yi can be summed together, and I see that I get minus 2 yi plus yi plus 1 equals mg divided by k. So this is just this is the same equation, just in a little bit cleaner form. And this thing is actually a numerical or a discrete approximation of second derivative operator. So this system is 1D Poisson equation. You may have not heard about Poisson equation, or did you? Laplace and Poisson equation. That's sort of stuff that like comes up later in calculus. It like involves typically multivariate calculus. It's very important in like engineering and solving PDEs. And there is like a lot of math around it. I will show you the 2D case in a second, where the math looks even a little bit scarier. In the continuous case, it's saying that the second derivative of the function has to be something. So it's an equation. The second, yeah. If you didn't have calculus, then I'm sorry. Then the derivatives might not be making much sense to you. But the message is good. That whatever this continuous math here is, this Poisson equations and Laplace business and so on, at the end of the day, it boils down just to a linear system. This is what I would like you to remember. There can be some scary continuous math to begin with, but after you, but you can convert it to just a linear system and solve the linear system. And all the complexity in the math is essentially just in the system matrix. So you don't have to deal with it. The solver will deal with it for you. It gets even more funny in 2D. And it's funny in both senses, that it's like there is some interesting mathematics, and it has also very cool applications. So in 2D, the Poisson equation employs the Laplace operator. Again, don't worry if you don't know these terms. The Laplace operator is nothing but a sum of two partial second derivatives. Again, this is something that comes up later in calculus. But I guess what I want to say is that Poisson equation can be used to model processes such as heat diffusion. So a simple example would be, I have like a metal plate, for example, like this. This is very cool, actually, that you can compute things like this. So I have a metal plate which has some boundary. These are the boundary edges of my metal plate. And I specify the temperature of the metal plate on the boundary. Right? So some temperature profile. So I don't know, here it will be, I don't know, hot, here it will be cold, here it will be different temperature, and so on. So I specify temperatures everywhere on the boundary. And I say that this will be fixed. And then I want to compute the temperatures everywhere inside, assuming this is like a nicely heat conducting metal plate. What will be the temperatures inside? Like this heat diffusion is a different way how you can look at it. You could also look at it as it's like a deformable rubber plate or something, and then I lift every point of the boundary by some amount, and I want to compute what is the interior doing. So you can like imagine sort of like a drum or something with some membrane, and I lift the membrane on the boundary and want to figure out what is the membrane doing inside. And the model I say is that inside the Laplace of my function is a 0, sometimes called Laplace equation. So Laplace means that the right hand side is 0. Poisson means that it can be internal non-zero, the right hand side. So the mathematics might look scary, but again, in the 2D case, just like in the 1D case, I can convert this. This is a continuous problem, right? X and Y are real numbers. I can discretize it. I can say that I have some nodes here and I have some nodes inside. So I convert it from infinitely many unknowns to finitely many unknowns. And then this scary looking formula, the Laplace's equation, becomes just a system of linear equations. System that looks like this. So phi is the function I'm looking for. In this case, discretized. So phi ij. So if I hit my square, here would be like phi 1 1. Here would be like phi 1 2, and so on. So this is essentially also like a matrix with these phis. And discretizing the Laplace operator. This is the discretization of the Laplace operator. What you can notice, it's nothing but the discrete second derivatives with respect to the x coordinate and with respect to the y coordinate. So let's take a closer look. So here I'm looking at y and j minus 1 and y and j plus 1. So this is moving in columns, right? So this is moving in the x coordinate. So this is the second partial derivative in x. That's this thing. The second, this corresponds to this. And here, what I have here, I minus 1j, ij is in the middle, and I plus 1j. So this corresponds to the second partial derivative with respect to y. I guess I was like making this look more scary. And the derivatives are basically nothing but locally linear approximations to a function. But I think it's still easier and maybe more intuitive to look at the discrete counterpart. And that's what it is. This is just one linear equation, right? Some question?
Yeah, so the discrete version approximates.
Exactly, yes. It approximates it, yeah. And approximates it better and better the more these nodes you have there, right? And there is like a lot of theory. It's in general it's called like finite element method, or there are actually two methods. You can do finite elements and finite differences. So here are finite differences. But in finite elements you can prove that if you will be putting more and more points, decreasing this spacing, right? Here this spacing between the grid points, if you'll be decreasing it, you will converge to the continuous solution. So looking at this equation, you can also rewrite it. You can rewrite it like this. Actually, maybe even better is to rewrite it like this. That's equivalent. So this is saying that this equation wants phi ij to be equal these four guys. So if I have, let me draw a picture. This is phi ij. This is phi I minus 1j. This is phi I plus 1j. Here is phi I j plus 1. And here is phi I j minus 1, right? So if I'm on the grid, there will be some other points here. If I'm on a regular grid, then this equation says that the value of phi ij is the average of these four values. It's the average of these four values. I sum them together and divide by 4. That's their average, right? So it's actually pretty intuitive what this thing wants, right? There are some four values. You can like look at them as heights, for example, right? That I have some stick from here, which is some height, a different height, another height, yet another height. And this thing wants to be in the average. It doesn't want to like stick out too much. Does that make sense? That's what this discrete Laplace equation tells us. So this Poisson, or this Poisson problem would be like a 2D version of the stretchy rope. If I had like some stretchy, I don't know, piece of rubber or something like that, then I can compute its deformations by solving the discrete Poisson equation, by solving the system of linear equation, subject to boundary conditions. I need these boundary conditions. In the rope, the boundary conditions were that the two endpoints of the rope were fixed, that they were attached to the wall or something. And subject to these boundary conditions, I can compute what are the values of the points on the interior that solve my Laplace or Poisson equation. This is actually super cool. Like in graphics, it has been used a lot because it produces very, very nice results. And the cool thing is that all you need to do to solve these things, after you set up the system, then you just need to invoke a linear system solver. And that will compute it. Yeah? So the question you are asking why this part of the equation is the same as the second derivative? Oh, why this is a second derivative? Ah, that's a great question. That is a very good question. How would I explain this? So I guess it's best to start with the first derivative, right? So if I have some function f from R to R, and I have some point on that function at some point, I don't know, x, then the derivative of f at x is the slope of the tangent line to the function, right? And how I compute the derivative, I look a little bit to the right, so I do some x plus h, where h is something presumably small, right? I take a look what is fx plus h, so if this was fx, here is fx, and here is my fx plus h. I do fx plus h minus fx, that's this length, right? And this length is just h, right? And I divide the two, so I divide, so this is this, and this is h. So I divide the two, and I get this slope. Well, here it should be like this. Actually, there is a reason, right? Because this the derivative is then defined as the limit of h going to 0 of fx plus h minus fx divided by h. It's actually cool that I still remember that. Thanks for asking me. So this is how derivative at x is defined. So notice that the limit, right? When I draw it here, it didn't really quite give me the derivative, right? I need to make the h smaller and smaller and smaller until I make it the smallest in the world, and then I will get the right derivative. That's what the limit says, right? You know this from some, that's basic calculus, right? So if I want to approximate the derivative in practice, if I don't have a continuous function, but I have only discrete points, right? Like that's what we are basically assuming here. So I don't really have a continuous function, but I only have some discrete points of that function, right? So if I want to approximate the derivative, then what I do, I just say this is, if this is like x1, x2, and x3, and if this is my h now, then I say that I approximate the derivative at x1 approximately, just like this, right? What do you think you should do? Just approximate it like that. Assuming that h is small enough, this will be close to what the limit would give me. So if I take like a really small h, I should basically get almost the derivative, right? Not exactly. But you know that we are not computing exactly on the computer anyway, right? So who cares? There will be some small error. Then I can also compute the derivative at x2 or approximate the derivative of x2, and I will get fx3 minus fx2 divided by h, right? That's the same thing, just done here, one point further to the right. And then what is the second derivative? Second derivative is a derivative of a derivative, right? So f second derivative is just taking the first derivative is a function, right? And then I differentiate it once again. That's what second derivative is, right? I differentiate it twice. By differentiating once, I get a different function. So I can differentiate again. That's what second derivative is, right? So if I know what is the first derivative at x1 and first derivative of x2, well, guess what I can do? I can approximate the second derivative at x2 as the first derivative of x2 minus the first derivative at x1 divided by h. Right? Now let's see if I got it right, and I will get the right formula, which is fx3 minus yeah, it will work. X2 plus fx1. Right? So here I took the the approximation of my first derivative, fx2, so I substituted this here, so that's fx3 minus fx2, minus this thing, minus fx2 plus fx1, that's because this is with minus. This is divided by h again, so it's divided by h squared altogether, and this altogether is 1 divided by h squared, fx3 minus 2 fx2 plus fx1, right? And this is the answer to your question. But I forgot where did I put it. It's here. That's this, right?
So shouldn't that be the same derivative as with respect to y?
I mean, if I'm looking at it as a matrix, then this is the row index and this is the column index, right? And if I'm moving the columns, that the columns are like this, right? So if I'm moving the columns, then I'm moving in the x-axis. That doesn't really matter, right? You have the y there anyway, right? So this is, actually this way is showing that this thing here is, this is called a finite difference approximation of the second derivative. And it's a linear expression. So if I say a linear expression has to equal some right-hand side, that's a linear equation. So those are like, I think, like the very basics of scientific computing, solving PDEs, partial differential equations. This is an example of a partial differential equation. But anyway, this the main point here was to illustrate that linear systems can do a lot of cool stuff. So here is just some, just like a rant about linearity. Linearity occurs sometimes very naturally in nature. Like I will later talk about light transport, about the radiosity in computer graphics. And light transport is linear, right? If I have one light shining at something and another light shining at it, they just add together. That's just how the nature works. And even if things are not linear, like the springs in the stretchy rope, the real springs are not really linear. But to a large extent, you can approximate them with linear things. So even if things are not perfectly linear, you approximate them with linear. And if things are highly nonlinear, then what you do, you need to do a nonlinear solver. And guess what the nonlinear solver will be doing? It will be iterating a linear solver over and over again. So the linear systems are really a fundamental cornerstone thing in scientific computing and a bunch of other areas. Another important feature of linear systems is sparseness. All these systems, coming up from some practical problems, they result in sparse matrices. What it means sparse, it means that the matrices have a lot of zeros. And by a lot, I mean that almost all elements there are zeros, except for a few that are not. And that means like typically asymptotically. It's not like having like a half of the matrix being zeros. That's usually not enough. If it's like a half of the matrix being zeros, you don't even need to talk about a sparse matrix. But if it's like, for example, a diagonal matrix, which is all zeros except for non-zeros on the diagonal, that's a perfect example of a sparse matrix, right? It usually won't be as sparse as that, but if it's like close to the diagonal, then we are dealing with sparse matrices, and we want to implement our algorithms accordingly. Because if you have a matrix that has like 99.9% of zeros, it would be very wasteful to store all the zeros in memory and then do all operations with the zeros, right? Instead, you can design the algorithm so they know there are zeros, and of course 0 multiplied with anything is 0, so you don't really need to multiply anything, you can just skip it. It's just that the representation of the matrices needs to be a little bit more sophisticated because it has to have some special cases for saying, here is block of zeros. The algorithms get then much more complicated. That's what makes the design of linear system solvers less trivial, is that exploiting sparsity. let's look at the stretchy rope example again. If I write down all the equations of the stretchy rope, so this was one of the equations of my stretchy rope, right? I showed you that this is again nothing but finite difference approximation of second derivative. And I have the two additional constraints that the 2 endpoints are, those are the boundary conditions. And if I write it in matrix form, I get this matrix formulation. This is the system matrix. And notice how the matrix looks like. I mean, it should be easy for you to verify that this is equivalent to this system. It's just the matrix way of writing it, or the MATLAB way of writing it. Right? If you want to solve it in MATLAB, you will have to prepare a matrix like this and then call a backslash. It's actually super cool. You can try it actually. It's super cool. That it's very, very simple to construct a matrix like this. It's very simple to come up with some right-hand side. And what you get as a solution is something interesting. Something not so simple. If you had to figure it out without the matrices, would be much more complicated. So my point here is that this matrix is extremely sparse. It's almost like the diagonal, right? It only has the elements on the diagonal. Those are these two extra ones and the -2k's. And it has only two non-zero bands here, or this is how it is called. Like just one off the diagonal. This is just two more strips worth of non-zero numbers, and they are all k on top of that. So here, everywhere else, here are zeros. Here too. You can notice that the matrix is also symmetric, right? So this, the 1D Poisson, or this is like a 1D Laplacian matrix, is an example of a bandit matrix. So this special structure of the matrices have names. This one is called a bandit matrix because these things are like called bands. So this is or tri-diagonal, I think, is the other term for that. So at most k entries away from the diagonal are non-zero. Turns out that actually this property is still that translates to LU factorization. If you do LU factorization of that matrix, lower and upper triangle, then you'll get something that has only non-zeros here and here. Everywhere else zeros. And the upper triangle will be like this too. Which is super important for computations. Because instead of n-cubed complexity, which Gaussian elimination or LU decomposition in general has, you now have just a linear complexity, right? Because asymptotically, the number of non-zero elements in the matrix is just O of n. So to eliminate it, I just need to do one sweep through the whole thing. The back substitutions, again, will just take one sweep to have a linear time algorithm. So this is incredibly faster. Doing this for 1 million vertices, if you want like really precise rope, if you like your life will be hanging on it, you want to do as precise simulation as you want, you can use 1 million vertices, no problem. You'll be able to compute that. If you wanted 1 million vertices cubed, no way, unless you had some supercomputer, and maybe even there it would be very difficult. So the point here is, if the matrix has a structure, like in this case the tri-diagonal structure for the 1D Laplace operator, then we can use it to our advantage. Okay, so that will be it for now. Next time I will show you the radiosity and some more cool things. Yeah, question?
On the last slide, the kind of matrices, there's one part of the multiplication
Oh, the previous one. This one?
yes. Does the multiplication come out so that there are zeros bordering it and zeros?
That there are zeros.
Like on top and bottom of that final.
Well, I mean, pick one of them, right? I mean, if you, I mean, just do it, right? So this one will come out to this is y1, so this would be y2. This would be y3, and this here would be y4, right? If I like multiply that together, like take that with it's not really in the matrix. I'm just how this would look like if you multiply it, right? So that's because this equation is only looking to the one to the left and one to the right. It does not look 2 nodes to the left, right? So if I am here, if I'm at I3, if this is I3, I'm only looking at I2 and I4. I'm not looking at I1 or I5 or anything else. So that's why there are zeros in the matrix. The zeros kill the elements I'm not looking at. Because every node is only acting by force from neighboring springs, and there are only 2 neighboring springs. So that's why there are zeros to kill all the rest. Okay, any other questions? Well, then I will see you on Monday, I think. Okay, have fun with project number 2. And submit project number 1 in time in the first place.